everyone, and welcome to today's webinar. The title of this week's webinar is Accessing the Array Database with the ZOS API using MATLAB. Today, I'll like to demonstrate how to use the ZOS API for accessing the array database. I'd like to show you what methods you would need to use and some tips and tricks on how to handle the arrays and the array segments with the ZRD Reader. During this webinar, I'm going to show you how the ZRD Reader tool works. I'll show you the conventional method, how to read in array database data, of course using the API and with MATLAB, and I'm also showing you the improved method that we've introduced with OpticStudio 16.5. And then I'd like to finish off with comparing the two methods regarding performance and speed. And at the end, you'll have the chance to ask questions, and I'll do my best to give you the answers. So first of all, thanks for joining me. My name is Thomas Pickering. I'm the product engineer for OpticStudio here at Zemax. Previously, I was a senior optical engineer here at Zemax, was in this role for about a year and a half. And before that, I was a postdoc working in particle beam instrumentation. I've got a degree in technical physics and a PhD in accelerator physics. And yeah, so also this year we'll be at Photonics West in about 2 weeks' time, and we'll be demoing OpticStudio and also lens mechanics. You can find us in booth number 1540. And yeah, come say hi. We're happy to chat, answer questions, show you what you need to know. And all right, let's dive straight in. The ZRD Reader tool is a tool to read the array database that you can get with any ray trace in a non-sequential mode. With the new tool, we've improved the way to process these files through the API. And to do this, we've made a DLL with C#. So we use this DLL to read blocks of array data into MATLAB all at once, rather than using MATLAB's own while loops to read in the data array by array and segment by segment. So because MATLAB's while loops are rather inefficient, we'll save a lot of time. So the processing time for a Zemax array database file in MATLAB is then comparable with the time it takes in C#, and it usually takes way under 5 seconds, whereas beforehand it would have taken you up to like 30 minutes, depending on the size of your array database. Before we can get started to read in the array database, I'll just like to make an array database, and to do this, I'll just use one of our stock files that we ship with the with OpticStudio. So I'm going to switch over to my OpticStudio. You can see I'm using 16.5 Service Pack 1. And I'm just going to open one of our example files. I'm going to go into non-sequential, miscellaneous, and I'm going to use the digital projector fly's eye homogenizer. Let me just open that. And we close this prescription data here. So you can see by default we will trace 1 million analysis rays. We don't really need this much, just to give you an idea on how this thing works. So I'm just going to change this to 1,000 rays, and then I'll go to Analyze, run a ray trace, and need to make sure to save the rays. And so I can see that we've saved 1,000 rays. I'm going to change this to this file name to R1K, and then click Clear and Trace to run my ray trace. 1,000 rays shouldn't take too long. And I'll also make one for 10,000 rays, just so we can have a comparison in time later on. So change the analysis rays to 10,000. Again, run the ray trace. Change the file name to 10K. And again, clear and trace. Okay, so now that we have a array database, we can go and read it in using the API. I've set up already examples, but the way to start with these examples would just be to go to programming, go over to the MATLAB button and select a standalone application. It will pop up just the MATLAB file, and we'll open MATLAB for you. And let's wait a little bit. Yeah, it would jump straight in, and basically you would take this standalone template to use to program your own application. So the way we start with this application, as usual, after some initial connection, initialization, we check that we actually have an application running, and then we start with the main body of the function, and after the main body, we clean up the connection and stop the application. Yeah, and within this function here, the begin application, we will now put our own custom code. I'm not gonna type it out for you. The MATLAB code will be you will be able to download it at the end of this webinar, so we provide it for you. But I'm just gonna, rather than typing it out, I'm just gonna show you the blocks of functionality that I've made. I've got this in this folder here. So before we start with this, I just would like you to just give you an overview of the functionality of this. So to read in a array database, the first thing you need to do is to open the array database reader tool. You need to select which array database file you want to use, and also apply filters if you want. We'll then run and complete the tool, then read in the results from this tool, and with these results, we then, to get the data from the actual array database, we need to read in the arrays in a loop, and we have to do this one by one. And then for each array, we need to read in the segments in a loop, also one by one. And after we've done this, we can use the data from these segments and arrays to calculate, for example, the total intensity. All right, let me show you how this works. So I'm going to switch over to MATLAB again. I'm going to close the standalone application and open the example that I've made with the conventional method. I'm going to maximize so you can see it a little bit better. Yeah, so the beginning block is the same. When we jump into the begin application, the first thing we do is we're going to set an object for the system that we work with. It's usually a primary system. And then I'm just going to set pointers, or I'm going to make paths or path strings for the lens file that I want to use, which is the digital projector flies homogenizer. And then I'm going to use make the same for the ZRD file that I would like to use. I'm going to start with the 1000 rays file, and then I'm going to pass these two file names into the function called read ZRD file. In this read ZRD file, first of all, I'm going to load the lens file. The only reason why I do this is to make the OpticStudio interface to be non-sequential rather than sequential. You could do this with a different method, but yeah, just for ease of use, I'm just going to load the lens file. Then I'm going to check if there are any tools currently open. For example, an optimization, a tolerancing. It's just a nice sort of like safe way for you to check the current state of your OpticStudio. If there is a tool open, I'll close it. Then I'll open the array database reader tool. I'll select the file that I've made. Yeah, so the 1000 ray file. I'll apply no filters this time. Then I run the reader and wait for completion. And then finally, I'll apply, I run the get results method to get my results. If I have results, I pass the results into this function called process ZRD2. And then after the process is finished, I'll just close my reader tool. This process ZRD Reader, process ZRD function is the main body of my reading in or processing the array data. And in the conventional method, as I mentioned earlier, it works like this. So we jump in, we start a timer, we set a few initial values. So we have this flag that basically shows us or tells us if we are at the end of our array database or if we need to finish our processing. We initialize the total segments that have been read with 0, the total arrays that have been read with 0, and the total power with being 0 as well. Is finished flag is set to true. We read in arrays, and we'll do this one by one. And to do this one by one, you have to use the read next result method. The return of this method are 5 values in an array. And because I'm not interested in, for example, the wave index or the wavelength in microns, I'm just going to use these variable placeholders that in MATLAB are these tildes. This is just a nice way to sort of like keep your code tidy, because if you don't use it, it's not necessary to use a variable and then afterwards clear it. If this method has been successful, which is in this Boolean called success, then we'll jump into the processing instead. Then we'll jump into the processing straight away. The array number will be written onto the total arrays read. The more arrays we read, the higher this number increases. We add the number of segments of this particular array to my total number of segments read. And then for each segment, so from 1 to the number of read segments, I'm going to read the segments one by one with the method read next segment, which is mimicking exactly the same as read next result. Again, there's quite a lot of return values that I won't be using in this particular example. For example, the X, Y, and Z locations, the LM and N ray directions, the energies, and so on. Sorry, the E fields and so on. I'm only interested in the success. So again, has it been read successfully or not, and the intensity of this particular segment. If this reading next segment has been successful, I'm going to add the segment intensity to the total power. And finally, if this hasn't been successful, I'll set the Boolean flag being finished to true, because then I have reached the end of my array database and I can finish my loop. And another way of ending the loop is if the array number is higher than a set number of maximum arrays, then again I'm setting the Boolean to be true. The number of maximum arrays are passed over, and I set it to, how much is this? 10 million arrays. This is up to you, and it's up to like the higher this is, the more time you might need to process this. And then at the end, I'll finish my timer, and I display the time with this talk. I'll display the total number of arrays that have been read, the total number of segments that have been read, and the total power of all the segments added together. Okay, so let's make sure we've got the right database. Yes, the 1000 arrays. And let me minimize this again. And I'm going to run this by pressing F5. And you can see when we run this, it might take a little bit. For 1000 arrays, it takes 1.4 seconds. You can see we've read in 1000 arrays. The number of arrays is 7,000. Sorry, the number of segments is roughly 8,000 segments, and we have a total power of 112. Okay, so we're going to use this to, first of all, yeah, it's been successful, but also we want to compare these results then to the new and improved method. Okay, so let's jump over to my slides again. So for the improved method, the overhead is pretty much the same. So again, we open the RAID database tool, we select the right RAID database file and apply eventual filters, run, complete the tool, get the results. The difference is now that we need to load the C# DLL, and then rather than reading in the RAID database ray by ray and segment by segment, we read in the data in blocks. The blocks you can define yourselves. This is a trade-off between speed and memory use. But yeah, so you have to set this yourself, and you will see this in a minute. And then afterwards, again, you can use the results to calculate the total intensity. Let's go back to our MATLAB, and I'm going to open the improved M file. So again, I'm going to maximize this for you to be able to see a little bit better. This is the same, so the overhead again is the same. I'm going to jump into my application. Again, I'm just creating pointers to, well, not pointers, but lens file and ZRD file paths to the correct Zemax file and the ZRD file. And then again, I'm going to pass it over to reading it. This again is pretty much the same. The only difference is that now I'm calling a function called process ZRD1 rather than ZRD2, but again, I'm going to pass the results from the RAID database reader. And I'm also going to pass over the maximum number of rays that I want to read, and again, I'm keeping it at 10 million. When you jump into the actual function, process ZRD1, the first thing we need to do, so again, this function uses the helper DLL to batch up the rays before processing in blocks. And the way I've set this up is I'm going to assume that the helper DLL is in the same directory as the .m file. And you can convince yourself that this is the case by being here. So I've got this ZRD loader.dll, which is again a compiled C# DLL, and this needs to be sitting in the same folder as my M file. Maximize again. So I'm loading the libraries from this DLL. Again, start my timer. And then I'm using this read ZRD data method, which is sitting inside this DLL, and I'm just reading ZRD data and the results. Then I need to configure the maximum number of segments that are being read at one time. Again, this is the trade-off between speed and memory usage, and I'm setting the maximum number of segments to be 10 million, and initialize this data block with this initialize output function. Again, I'm setting the beginning flags being false, the total number of segments read being 0, and same with the total number of rays, and the initial total intensity is also set to 0. I'm running a while loop until a certain boolean is set to true. So yeah, and in blocks, I will now read in the ZRD data. So you can see here I'm using the function read next block, and yeah, so I'm reading blocks of 10 million segments. If this block contains data, then we'll jump into the else case here. So we read out the number of read segments and add it to the total number of segments read. To get the total number of rays that have been read, you need to be careful a little bit, because arrays in MATLAB start with 1, arrays in .NET start with 0. So we'll have to subtract -1 from the number of read segments to get the correct ray number. So now we can retrieve whatever data we want to use. Again, I want to use the intensity data, but you could also use all the x coordinates or all the y coordinates and so on. And then finally, I'm summing up the intensities from all the segments that have been sitting in this block and add it to the total power. At the end, again, if my total number of rays that have been read is larger than my manually set maximum number of rays, then again I'm going to jump out of the loop. At the end of the loop, I'm stopping my timer and again displaying my results. Okay, so let me minimize this and run the method. So by pressing F5, even just with 1,000 rays, my lapse time is now dropped to 0.2 seconds. You can also see that just for a sort of sanity check, the number of rays is the same, the number of segments is the same, being just about 8,000 segments, and also the total power is the same. Yeah, so you can convince yourself that this is exactly the same data that's been read. So this is for 1K. I'd like to compare the same for the 10K case that I also made. So we're going back to our conventional method. I'm going to change the file path for the ZRD file to being 10. Control S for saving, pressing F5. Yeah, I'm running it. It might take a little bit longer. Okay, so it's taken 13 seconds to read in 10,000 rays with 80,000 segments. And I'm going to do the same for the ray database improved reading. So again, I have to go up, change my ZRD file to being 10K. Run by pressing F5. And you can see that my time is still about 0.2 seconds or 0.15 seconds with the same results as previously, but much, much faster. I'm not going to do the same for the 100,000 rays case, because as you can imagine, it would take about 2 minutes in this case, but we can just jump over to a little comparing performance. So you can see that in the conventional method, using just your normal MATLAB loops, you increase about a factor 10 pretty much for every, in this particular example, for each factor of 10 in rays. And the processing time using the new DLL, you will stay pretty much always like in the second order of magnitude. Okay, I've come to the end of my webinar. So thanks very much for attending. I'll try to answer all the questions that you have. And if you don't get your question answered, then please, you can email us at support@zemax.com and we'll do our best to answer them. So I've just had a question coming in about how to find the available methods in the interface, specifically for MATLAB, and where to find documentation. So at the moment, the interface documentation, when you go over to MATLAB, can be found in the in programming, it's the interface documentation here. The interface documentation at the moment, unfortunately, is, so for example, if you go and check the help for, let's say, read next. Sorry, where were we? So for read next result, copy it in. So unfortunately, at the moment, the interface documentation is only for C#, Visual Basic, and C++. The one that's closest to MATLAB is C#. Yeah, you would just drop the definition, the type declaration, and everything else is pretty much used in the same way. Other than that, I can just all I can say is use the examples that have been provided. And if you have any questions of how to use a function, just drop us an email and we'll be more than happy to help you. That's currently how it stands with the support for MATLAB. Are there any other questions? Okay, so if there aren't any more questions, oh, hang on. There's just a question coming in about filtering the arrays with respect to a defined coordinate. So all you would need to do is using basically you can read in the data using this type of setup, and then you would need to filter or create your if cases. Or what you can also do is if you don't even want to read in all the arrays that you need, all the arrays that are present, you could just use this filter tool here, so you can filter the arrays with respect to what you would want. The filter strings work exactly in the same way as they would use in the user interface. Yeah. One of the questions is, can we, if we're posting these MATLAB programs on the web, yes, we will do this. Same with the DLL. So all you need to do is download it, copy it into your folder, and you can run it. There was also a question about if we're able to use MATLAB to run ZPL macros. The API does not support running ZPL macros. You would have to translate them into API functions to make them usable. There's also a question if there's a way of calculating y cosines of rays to find out if the rays are collimated. Yes, you can do that. For each ray that you can read in, you can get your direction cosine, and with this you can, with a little bit of trigonometry, you can calculate if your ray angle of incidence makes them collimated or not. If you have any further questions, please send them to support@zemax.com. And again, thanks for joining, thanks for listening, and see you next week.